Hello everyone. So in this video we will discuss that how we can find the maximum value in a binary tree, and we'll discuss an algorithm which is recursive in nature. So here you can see, let's say we are given with this binary tree having nodes as 4, 3, 7, 5 and 8, and 4 is at the root. So let's say we want to find the maximum value inside this binary tree. So looking at this binary tree, we know that 8 is the maximum value. But how to find whether 8 is the maximum value in this binary tree is using this algorithm, which is recursive in nature, because here you can see the method name is findMax, which takes in a root, and inside that it again calls findMax. So here findMax method is calling itself at two places, at line number 6 and line number 7. So therefore this algorithm is recursive in nature. So here the idea behind finding the maximum value in a binary tree is, let's say we know the value of root and we know what's the maximum value in the left subtree and what's the maximum value in the right subtree. So we can simply compare the maximum value of the left subtree with the root's value, and then we can compare with the maximum value of the right subtree, and we can come to know what's the maximum value among these three values. So this idea can be applied on each and every node recursively. So for example, if you want to find the maximum value of this binary tree having three nodes as 3, 5 and 8, we can simply take the root's value. Then we need to calculate the maximum value of the left subtree and the maximum value of right subtree, and we need to simply compare these three values and we will get the maximum value till this node. So this algorithm is recursive. We need to apply these three steps on each and every node. And using this algorithm, we will also traverse each and every node, because in order to find which is the maximum value among this binary tree, we need to traverse each and every node. So let's see the demonstration of this algorithm step by step, so that the idea of finding the maximum value inside this binary tree will be more clear to you. Also here you can see, as this algorithm is recursive in nature, when findMax will get executed, it will internally call again the findMax. So in order to keep the track of these methods, we will create a table which will be nothing but our call stack. So let's see how this algorithm and this call stack works together. So at the first step, we are calling the findMax method and we are passing in the root of the binary tree whose maximum value we need to calculate. So on the call stack, you will find one findMax method whose root is pointing to a node having value as 4. So here you can see that this table has 5 values: line number, root, result, left and right. So as the algorithm is recursive in nature, when we will leave this findMax method and we'll again call findMax, we'll simply keep the track of the line number here. We'll keep the track of the root, result, left and right, which we will see later how they are important. Moving ahead. So here, as the algorithm is recursive in nature, we need to provide a base case so that we can exit from the algorithm. If we don't provide this base case, then this findMax will again call findMax and it will go on, because there will be no end. So we need to provide this base case that if the root is null here, then we can simply return the minimum value from here. So for example, if the root is pointing to null, so we will simply return the minimum integer value, because null can signify that this is the minimal value. As the return type is integer, we need to return a value. So we'll simply return the minimum value of the integer, because the minimum value of integer won't affect the maximum value of this binary tree. So here currently we are providing a check that if root is equal to null, then simply return the integer's minimum value. So currently root is pointing to 4, therefore this condition comes out to be false. Also friends, we discussed the idea that how we can find the maximum value of any node and its left and right children is finding the maximum value of its left subtree, finding the maximum value of its right subtree, and comparing it with the roots value. So here this 3 line will do that. In the result, we are simply storing the roots value. So here in the result it will be coming as 4. Moving ahead. So now we'll traverse to the left of this binary tree in order to find the maximum value of the left subtree. So we are simply again calling the findMax method, but this time we are passing in roots.left. So root is pointing to 4 and its left is pointing to 3. So 3 will be our new node. And here you can see we are leaving this findMax method at line number 6. So we'll simply keep the track of line number here, so that when this findMax will end, we know that where to start this findMax. So we'll simply store the line number, which is 6. And we will again call the findMax method passing in roots left node. So on the call stack it would look that findMax method is called. We have left this findMax method here at line number 6 and we are again called findMax, and this time the root is roots left, which is 3. So now root will point to 3. Moving ahead, root is not equal to null. Again we will apply the algorithm recursively on this node. So first we will store the roots data, so which is 3. Now in order to find the maximum value till this node is, we need to find the maximum value of its left subtree, we need to find the maximum value of its right subtree, and we need to compare those values with the roots value. So first we will go to the left of this root. So we will call findMax again, and this time we will pass roots left, which is 5. But we are leaving this findMax method, so we'll simply keep the track of this line number, so which is 6. So now findMax will be called again with roots left, which is 5. So our new root will become 5. Root is not equal to null, so this condition comes out to be false. And now we'll apply our algorithm recursively to this node. We will first store the roots data in the result, which is 5. And then we will again call findMax method to simply calculate what's the maximum value of its left subtree. And we are leaving this findMax method at line number 6, so we'll simply store line number 6 here. So there will be one more method on the call stack, but this time the roots value will be null because 5's left is null. Here we are calling roots left, so roots left is null. So now root will point to null. Here we will check whether root is equal to null or not. So here you can see that we have encountered a base case that root is equal to null. So here we will simply return the minimum value of the integer, because as roots left is null, so there are no more nodes to traverse, and we will simply return the least value of the integers, which is integer's min value, whose value is this. Because this value is negative in number, therefore it won't affect the maximum value of this binary tree. And as the left child is null, so we can simply return the minimum value of the integer. So we are returning the integer's min value. So here you can see that we are leaving this findMax method here. And once we leave this findMax method here, this call will go to this method, because this findMax method had called this findMax method. And we also know that we had left at line number 6, so we'll start our execution from line number 6. And as we are returning the integer's min value, so this findMax method will get that value. So it would look something like this. This method will be removed from the call stack. Execution point will reach here. We will start our execution from line number 6 because we had left this method at line number 6. And here you can see whatever the value this findMax method returned, we will simply store in this integer variable left. So which was the integer's min value. So in the left we will simply store the minimum value of the integer. So I am simply denoting it by imv here. And when we were executing this findMax method, here you can see root was pointing to 5. So again root will point to 5. And we will proceed ahead with this method. So here you can see we have this roots value which is 5. We have calculated the maximum value of the left. Now we will calculate the maximum value of the right. So we'll again call the findMax method, but this time we'll pass the roots right value. So here you can see that we will again have to leave this method at line number 7 this time, and we will call findMax method again, passing in roots right which is null. So it would look something like this. Line number is updated here. FindMax method will be called, and there will be one more method on the call stack with root as null. So now root will point to null. And why this root is pointing to null? Because we have called findMax method by passing roots right, which is roots right is null. So here now root is equal to null. So we'll simply return the minimum value. And this method will be removed from the call stack. And the execution point will reach again on this method. And we'll start our execution from line number 7. So this method returned the integer minimum value, which will be stored in the right here. And when we have left this findMax method, root was pointing to 5. So now root will again point to 5. And the execution will continue from here. So here you can see now we have got all the 3 values to compare. The roots value, the maximum value of its left subtree, and the maximum value of its right subtree. So now we can simply perform this comparison for this node. So here we'll check whether left is greater than result or not. So left value is the minimum value of the integer. So therefore this condition comes out to be false, because value of left is integer's minimum value and result value is 5. So 5 is greater than left. So this condition will come out to be false. We'll check whether rights is greater than result or not. So rights value is also integer's minimum value. So this condition also comes out to be false. And here you can see that among this node, the maximum value is of the root, which is 5. So we'll simply return 5 from this findMax method. So now here you can see this findMax method will be removed from the call stack, and the return value will be 5. So this method will be removed from the call stack. The execution point will reach here, and we know that we have left this findMax method at line number 6. So we'll start execution from line number 6. This findMax returned the value as 5. So this 5 will be stored in the left variable here. And when we left this findMax method, root was pointing to 3. So now root will point to 3. Moving ahead. So friends, for root 3, we have already calculated the maximum value of its left subtree, which is 5 here. Now we need to simply calculate it for right subtree. So we'll again call findMax method, and this time we'll pass roots right, which is 8. So we will be leaving this method at line number 7 here. And there will be one more method on the call stack with now new root as 8. So root will point to 8 now. We check whether root is equal to null or not. So root is not equal to null. We will store roots data, which is 8. And now similarly we'll perform this recursive algorithm for the root 8 now. So here you can see friends, these 3 steps we need to perform on each and every node. So what we did for 5, now we'll again do it for 8. So we'll simply go fast here, because we already seen what happens when the nulls are encountered. So first we'll update the line number, which is 6. And there will be a findMax method in the call stack, because now we are going to roots left. So roots left is null. So this findMax will be called with null value. Root will point to null. And root is equal to null. So we'll simply return the integer's minimum value. And this method will be removed from the call stack. And integer's min value will be returned to this findMax method. So it would look something like this. We'll start execution from line number 6, where root will now point to 8. And the integer's minimum value, which was written from this findMax method, will be stored in the left here. And similarly now we'll go to root's right. So we'll update the line number here. So findMax method will be called again with the root as null. Root will be pointing to null. And here root is equal to null. So we'll simply return the minimum value of the integer. So this method will be removed from the call stack. And this method will start execution from line number 7 now, where root will now point to 8. Because when we left this findMax method, root was pointing to 8. So root will point to 8 now. And the integer's minimum value, which was written from this findMax method, will be stored in the right now. And now as we have got these 3 values to compare, we will check whether left is greater than 8 or not, because we need to find the maximum value. So left is not greater than 8. So this condition comes out to be false. Right is also not greater than result, because right is storing the integer's minimum value and 8 is greater than this value. So this condition also comes out to be false. And we'll simply return 8 from this method, because we have found the maximum value of this right subtree, which is 8. So we'll simply return 8 from this findMax method. So this method will be removed from the call stack, and the execution point will reach to this method, where we had left at line number 7. So we'll start from here. And here root value was 3. So now root will point to 3. And we know that from the right, we return the value which is maximum as 8. So 8 will be stored in the right here. So friends, here you can see for this small binary tree, we got the 3 values. 5 was the maximum in the left subtree, 8 was the maximum in the right subtree, and we'll simply compare it with the root, which is the result value. So here we'll perform the comparison. So we'll check whether left is greater than result or not. So this condition comes out to be true, because left value is 5, which is greater than 3. So we'll simply update the value of result with the maximum value, which is 5. So this will become 5. We'll check whether right's value is greater than result or not. So value of right is 8, which is greater than result, which is 5. So this condition also comes out to be true. So we'll simply update the maximum value, which is 8, into the result. So this will become 8. And then we'll simply return 8. So from this findMax method, we are returning 8, which is the maximum value among these 3 nodes. So this method will be removed from the call stack. And this method will start execution from line number 6, where root was pointing to 4. So root will now point to 4. And the value which this findMax method returned, which was 8, will be stored in the left. So here you can see that for the actual root of the binary tree, we figured out what's the maximum value in the left subtree, which is 8. So now we need to simply find the same for the right subtree. We'll start our execution from line number 6 again. And now we'll simply go to its right subtree by calling the findMax method and passing in the root's right value, which is 7. So this method will be removed from the call stack and we'll simply store the line number 7 because we need to keep the track of this recursive nature algorithm. So line number will be updated as 7. There will be one more method findMax having the root point to 7. Because we have left from line number 7 passing in root's right value. So root was 4 and its right value is 7. So 7 will be our new root for this findMax method. And friends, similarly, we will apply this algorithm recursively on this node now. What we seen with 5 and 8. So we'll simply quickly go over this algorithm. Root is not equal to null. We'll store the root's value in the result field, which is 7. We'll recursively go to the left subtree now here by passing in root's left. As we are leaving at line number 6, we'll store line number 6. There will be new method on call stack with root pointing to null now because we are going to its left now. So this root will be null. And we'll simply return the integer minimum value from this findMax method. We'll start our execution from where we left at line number 6, where root was pointing to 7. And the value which this findMax returned was integer's minimum value. So we'll simply store in the left. And similarly for the right, it will perform the same. We update the line number here. We leave this method. We again call findMax with root's right, which is null. So there will be one more method on the call stack having value of root as null. So root will point to null. We'll simply return the integer's minimum value because root is equal to null. So this method will again come on the call stack and will start execution from line number 7 now. So here root will now again point to 7. And this method had returned integer's minimum value, which will simply store in the right here. And now we'll simply compare these three values, 7, left and right, and we know that 7 is the maximum value. So these two conditions will come out to be false because left is not greater than result and right is also not greater than result. So this both the condition will come out as false and will simply return 7 from this findMax method because 7 is the maximum value of the right subtree for the actual root. So this method will return 7. Execution point will reach here. We had left at line number 7, so we'll start executing from line number 7, where root was actually pointing to 4, so root will point to 4. And the findMax method which got executed before this findMax method returned value as 7, so 7 will be stored in the right. So here you can see, for this complete binary tree, now we have actually got all the three values. The root's value, the maximum value of the left subtree, and the maximum value of the right subtree. So we'll simply compare these three values and get the maximum value of this binary tree complete. So we'll check whether left is greater than result or not. So value of left is 8. It is greater than result, which is 4. So we'll simply update the value of left into result. So result becomes 8 now. We compare whether value of right is greater than result or not. So right value is 7, which is not greater than 8. So this condition comes out to be false. And finally we will return the value 8, which is the maximum value among this binary tree. So this method will terminate here. And on the call stack this will get removed, returning the maximum value of this binary tree, which is 8. So friends, here you saw a very long demonstration of this algorithm where we applied this algorithm recursively on each and every node to find what's the maximum value of the binary tree. So friends, the complexity is involved in this recursive nature, which we demonstrated using the call stack. And once you understand how this call stack works, you can simply code the algorithm related to binary tree recursively. Now let's go to IntelliJ and see the working of this code. So friends, I hope you have liked this video, and in case you have liked this video, then please like, comment, share and subscribe my channel. Thanks, have a nice day.